All right, there, geometry people. I'm going to try to chunk this down into very digestible parts and try to go fairly quickly, but I also want to make sure you have this as reference as you're kind of studying over the next couple days for a final test of the semester, of course, minus the final exam, which is I'm gonna have some pretty good news about that final exam here coming up next week. Um, so stay tuned. But anyway, let's jump into this first part of the review. Now, this is about transformations, and granted, we haven't talked transformations in quite a long time, but you should have pretty extensive notes about transformations, in particular rotations, translations, and reflections. So one part of the study process, certainly going back and getting those notes, and if you don't have many more, scroll down the Edmodo page, go back on the YouTube channel, and see if you can locate those Cornell note pages, because that's going to help refresh your memory on all this stuff. But anyway, let's get to it. So the first one, or the first thing we have to execute here, is a transformation by this rule. And this rule is really important to kind of take note. These rules are informative. Now, this first letter, this guy right here, which I'm going to kind of circle, um, don't pay too careful attention to this because everyone kind of uses a different letter to identify the transformation. In this case, this T does stand for a translation, but there's actually a much better way to tell it's a translation without looking at that letter. Like, it's really not that important. The important part is actually this piece, the part that I way missed when I tried to highlight. Whoa. Okay, that part right there is actually the piece that tells you it's a translation. Because what they're saying by this notation that I highlighted in red is that this is the important part of the transformation I want you to execute. In this particular case, taking note that these two kind of little chevrons here at the end indicate that whatever is inside of is a vector, and a vector is something that has distance and direction. What this really tells you is that I want to take this xy value, whatever you got, and I want to add 4 to the x, and then I want to take 6 away from the y. Because, of course, if you kind of consider that a coordinate xy is arranged in that manner, that's all that vector tells you. So think about this. If I'm adding in one direction and subtracting in the other, what do I really have? Well, in this case, I do have a translation. And of course, the kind of maybe what you called in the past in terms of translation is just a slide. And if you think about moving an x value to the right and down, well, you're actually just sliding. So we have a couple of different ways we can execute this. One pretty precise way, one extremely imprecise way. The precise way is to do kind of a point-by-point analysis, and here's what I mean. So take this value of c right here, which I just highlighted in red. Consider the coordinate of c is negative 5, comma 0. So if I want to take this vector and apply it to that coordinate, I can. So coordinate c, which was negative 5, comma 0, becomes plus 4 and minus 6. So that's going to be a negative 1, negative 6. And again, I'm getting that because the vector is 4, comma negative 6, which means I'm going to move the x plus 4 and the y minus 6. All right. So tracking that on my here grid, this negative 5, 1 is going to be negative 1, comma 1, 2, 3, 4, 5, 6. Okay, and that's going to be my C prime. So I'm going to move the other ones the same way. I'm going to go ahead and switch colors here. So if I consider this B as my pre-image point, that point looked like it was at negative 1, 6. So it was at negative 1, positive 6. So after my vector transformation of plus 4 minus 6, that's going to be as a 3 and then comma 0. So let's see, 1, 2, 3, 0 for B prime. And we'll go ahead and do the same thing for A, and I'll go try to go a little faster here. Okay, so the A coordinate was 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be at negative 7, comma 8. So negative 7, comma 8. So if I underlay that, excuse me, I slurred my word there. So if it undergoes this transformation of plus 4 minus 6, I will end up at negative 3, comma 2. So negative 1, 2, 3, 1, 2, and that's my A prime, okay? So once I fill in or connect the pieces here, connect the dots, what I should have is a translation of 4 units to the right and 6 units down. Now, I said there was probably a little bit simpler way to do it, albeit somewhat inaccurate, but again, you're just trying to get an idea of the transformation. I'll be really honest, I'm not super concerned that you guys can replicate this perfectly on the grid. This is more about recognizing what you got. So when I say there's an easier way to do it, with digital ink, we actually can just do a movement here. So the vector is 4 to the right and 6 down. So 1, 2, 3, 4 to the right, and then 1, 2, 3, 4, 5, 6 down. And so I can kind of confirm for us that what we did have here is a translation, a slide. All right, so moving over to this one. And again, I caution you to not really pay too careful attention. Come on, focus up there. I wouldn't pay too careful attention to the letter that's being used, but much rather look at this important information. I have a point and I have an angle. So what I really have here is a center of and angle of rotation. Okay. I had a student come to me today and say, "Well, Mr. Collins, are you sure? Like, didn't we just use like little r for rotation and like a p thing for reflection?" Don't worry about that. What you need to focus on is the important information. Okay, and that's going to kind of tell you what transformation you're looking at. So this is going to be a rotation of 90 degrees, and I left this little note here because it has been a while since we talked transformations at all. Man, look how long it's taken to focus in. Come on, you can do it, iPad. You can. There you go. I want to kind of remind you that rotations are counterclockwise. So here's the interesting part. Um, the easiest way to kind of consider how to make this rotation, just like we made this translation, is to think about the point. So instead of trying to move the whole object, I'm going to just try to move like a point at a time. Okay? So the that kind of mentality I'm going to take to this as well. So what I mean is this: instead of trying to move the whole object, I'm going to reduce this down just to moving points, and I'm going to move C first, and I think you'll see why I'm moving C first here in a moment. An important thing to note for this rotation is that I do have this center at 0, 0. What that means, and most importantly, that that is the only point, the point I marked in red, the center of rotation. This is the only point that will not be moving through this rotation. Everything else will. So if you're looking at your work and you're seeing that C is actually still where it is after your rotation, you're going to have a bad time because the center of rotation, even though being off the triangle, means the entire triangle is going to move. So what I need to do is actually move C 90 degrees counterclockwise. Counterclockwise is, of course, like that. So I propose that C actually moves 3, 4, 5. C actually moves right here. That's going to be, and I'll actually put that back in green, and that's going to be my new C prime. I can confirm this a couple different ways. Number one, considering that the angle of rotation is 90 degrees, if I consider the angle formed between the pre-image, the center of rotation, and the image, two things have to be true. One, it has to match my angle of rotation, which it does. And the second thing is I have to make sure that it's the same distance from the center of rotation as it was to my image. And it is, because you can actually count, which is why I wanted to move C first, because it demonstrates that point very quickly. So you have the angle formed between the pre-image, the center, and the image have to be my angle of rotation. And also these distances here have to be the same, which is ultimately how you tell us a rotation. So when I'm moving B, I can take kind of the same tactic. If I consider, ooh, that's not a perfectly straight line. Let me try that one again. So if I consider this length right here, I have to replicate that out to B prime, but I have to make sure the angle is also 90 degrees. So if we do this a really quick count here, 1, 2, 3, 4, 5, 6. So what I'm actually going to do, instead of going left 1, up 6, I'm going to go down 1 and over 6. So down 1, 1, 2, 3, 4, 5, 6. Which, if you kind of review your notes, that falls in line with the algebraic rule we discovered for rotations. But again, important thing to point out that these are actually going to be the same length, and of course the angle in between is going to be 90, and that's going to be my B prime. Okay. So one last one, let's talk about A. Okay. So again, the distance from A to my center of rotation has to be the same out to A prime, and the angle formed between A, my center, and A prime has to be 90. And I think we can use a grid to help us count this out. Let's take a look here. Wait, 1, 2, 3, 4, 5, 6, 7. Okay, so instead of going left 7 and up 8, I'm going to go down 7 and left 8. Okay, so 8 prime is right there. Okay, so again, we have 90, and then we can fill that in. Okay. So again, kind of the quick way would be to say like trace over this triangle and kind of move it using digital ink. But this is equally as good, and it's important to note we notice the rotation again for two different reasons. One, the angles formed between the pre-image, the center, and the image are all 90, and the distance from the pre-image to the center and the image to the center are the same exact length, right? So there we have a rotation. I don't know if I wrote that or not, but I'm going to go ahead and, oh yeah, I did write it there. Okay. Two more, and it's going to go a little bit faster. These are a little bit more simple. Again, the thing to note, again, is not the letter because I think we're used to seeing this as like a row. But I'm using a small r here because that's also another way to say it. The thing to take note of is actually this guy right here. And what this tells us is that if I'm just giving a line, this has to be a reflection. In fact, this is going to be the line of reflection. Now, y equals x caused some controversy. Y equals x is nothing more than a y equals mx plus b equation. In this case, y equals x, which tells me that I have a slope of 1 and a y-intercept of 0. So what that line looks like is actually a line of slope 1 crossing through the origin. So it's going to look like this. This is actually y equals x. Okay. Now, if you're unsure how to graph that, you probably want to stop this right now, go click on a YouTube video, go find one in Khan Academy, something that explains to you how to graph this line, because that's something. Oh, sorry about that. I have no idea how long that's been up, and I apologize. So that blocked part of the video, I'm sorry. So let's catch back up. Um, and if it blocked part of this one without me knowing, because I wasn't looking at my computer screen, that is the final version of that one. Okay, so you can pause the video and copy that down if you need to. Anyway, as I was saying, so we have this slope, y equals x line of reflection. That slope of 1, y-intercept is 0. So we have to reflect this beast. And so this one I'm going to do a little bit less precise. But certainly the one thing we have to observe is that we do need a perpendicular bisector that runs in between my pre-image and my image. So what I mean is this. And this is going to be a really, really quick version of this because I'm not going to, because I'm kind of running long here. But what I mean is that the location of C prime, wherever it ends up being, which is approximately right there, uh, it has to be the same distance. In fact, I think C prime is a little too far. C prime is going to be a little closer to right there, actually. Um, so C prime, okay, C prime has to be a perpendicular bisector with my, excuse me, with my line of reflection, which is this y equals x line. Okay? All right. So if I'm looking at B prime, I'm going to kind of take this the same way. So B prime is pretty close to right there. Okay. Again, we're looking at a perpendicular bisector, and C prime is going to be the same way. Eight. Okay, so we have a perpendicular bisector to A prime. So that's not a perfect version. It's fairly close. I was counting really quickly there because I realized how long this video is getting. Um, but there you have it. That's going to be my reflection. So those are the three that we dealt with before. I've now kind of thrown a curveball at you, and I want you to evaluate this. Now, this is not something to freak out about. This is just a pure algebraic rule. Next semester, we'll get more in depth into kind of what this is all about. So this is a purely algebraic rule. So what this is saying, 7, 8. Okay, so what this is saying is if I have this coordinate that's negative 7 comma 8, I want it, so the new coordinate is going to be half of each of those values. And so in that case, A, which was negative 7, 8, will go to A prime, which will be negative 3.5 and 4. Again, I'm just taking half of the coordinate values. So B, that was negative 1 comma 6. Okay. it will now end up at b prime, which is going to be negative zero point 0.5 comma 3. Again, just taking half the coordinates, okay? And so we have negative 5 comma 0 for c will turn into c prime, which will be negative 2.5 and 0. So if I'm going to go ahead and graph these things, a is going to be negative 2.5, 1, 2, 3, 4. So that'll be my a prime. B prime will be negative half comma 1, 2, 3. And C will be negative 1, 2.5 comma 0. And so that will end up being my C prime. So this is actually my new transformation. Now, this is going to be none of the transformations I've seen before. And so it is important to examine why. And I think the glaring difference between all of them, besides having a different rule, but they all kind of have different rules, is if you look at the pre-image and the image, you'll notice on this one, the pre-image actually ends up being smaller. So even though I followed a rule that I was given, it still ended up as a smaller object. And that ultimately is a difference between a rigid and a non-rigid transformation. So if I think about the term rigid, what that really means is that if I have this pre-image and I take it to this image through some transformational rule, in this case a translation, in this case a rotation, or in this case a reflection, what I started with and what I ended with is ultimately congruent. I haven't actually changed anything. But if you look at this one, and I can tell you this is something called a dilation, this is a non-rigid transformation for just the same reason. I did transform my object using a particular rule, but it ends up smaller. And that's the difference between a non-rigid and a rigid transformation. So that one went a little bit long, guys, but that one was a fairly complicated, pretty in-depth one. So I'll try to keep the video shorter for the rest. So please use this for study, and I will see you guys in part 2.